All right, at the end of week 11, we started discussing the number of terms in an expression. So we said that terms are separated by addition and subtraction signs. Now, it's important to identify and combine like terms before we decide how many terms an expression has. And we should also be able to distinguish that terms are not the same as variables. So, based on our conversation, we said 2xy has two variables. The variables are x and y. But it is only a single term because there are no addition or subtraction signs. Now, x plus y has one variable, and it has three terms, but two of them are alike, this x and x. So I can combine the x and x through addition. X plus x is 2x, and I'll get 2x plus 1. 2x plus 1 has two terms, and those two terms are unlike. If we continue to look at examples, we see that 2x plus 2y plus 2xy has two variables, and those two variables are still x and y. But there are no like terms. Because there are no like terms, I can't combine anything. This has three terms. If we could combine 2x, 2y, and 2xy to get 6xy, then both sides of the equal sign should be the same when we evaluate this expression for different values of x and y. Now, the values of x and y that I've selected are x equals 3 and y equals 5. And it's always okay to pick values of the variables to see what happens when you simplify the expression. So here we have 2 times 3 when x equals 3, plus 2 times 5 because y equals 5, plus 2 times 3 times 5, which is 2xy. Now, if that's equal to 6xy, then I get 6 times 3, which is x, times 5, which is y. Now 2 times 3 is 6, 2 times 5 is 10, 2 times 3 times 5 is 30, and 6 plus 10, 16, 16 plus 30 is 46. 6 times 3 is 18, and 18 times 5 is 90. 46 is not equal to 90, and because 46 is not equal to 90, both sides of the equal sign are not actually equal, and we didn't combine terms correctly. So here, we saw this, we tried to combine terms that we thought were alike, but these terms are not alike. They're all separate terms. This x term is different from this y term, is different from this xy term. Now, here comes the fun part. Each of these expressions can be named by the number of terms and the degree. So, when we're thinking about the number of terms, we want to keep this sort of suffix in mind. So the ending of the word, this suffix, nomial. And so when someone asks you about the number of terms, you know you're saying something about a nomial. So mono means one, and when we put this mono together with nomial, we get a monomial, which is one term. Here we have bi, and bi means two, and when we put these together, we get binomial, and we see that binomial has two terms. Here, tri, like tricycle, tricycle has three wheels, tri means three, and we get trinomial, which is three terms. Now, we could go on forever, 4 terms, 5 terms, 6 terms, but we want to generalize this by saying poly, and poly means many. So when we have a polynomial, we have many terms, or one or more terms. Now, if we want to look at this again, we can say a monomial is a polynomial with one term. We can say a binomial is a polynomial with 2 terms. We can say a trinomial is a polynomial with 3 terms. And we're specifically naming this thing by the number of terms that it has. If it has 4 terms, we're going to call it a polynomial for the sake of generalizing anything above 3 terms. Now, the degree is a little different. When we think degree, we should be thinking about exponents, and we're looking at the power. So in most cases, we're looking at the power on a variable. So the degree of a term has something to do with the power. Now, if we think about a constant, a number with no variable, such as 6, okay, we see 0 variables, and it actually has a degree of 0. Now, we can think back to our exponent properties and say, oh yeah, x to the 0 is equal to 1. So we could actually say that this was 6x to the 0. And since x to the 0 is equal to 1, we get 6 times 1, which is just 6. So this constant has a degree of 0. And we can see that again because x to the 0 is equal to 1. Now, 1 is a constant, so constant, 0 variable, 0 degree. Now, the next one that we're going to look at is what's a first degree. So a first degree we're going to call linear, and we have a variable with the first power. So our first power just means that we have an exponent of 1, and so x to the 1 is linear. It forms a line, and when we think about a line, we just think about sort of one part, and we have a first degree. Now, for our second degree, we're going to call it quadratic, and we're going to say a quadratic has a variable with the power of 2. So x squared is a quadratic term, and when we think quadratic, it's actually nice to think of quad. Now, when you think of quad, you think 4, but if you think about a 4-sided figure, which quadratics form, squares, okay? If you think about a 4-sided figure, it only has 2 dimensions. And so we have this base, which is a horizontal dimension, and we have this height, which is a vertical dimension. And so we have 2 dimensions. So when we think quadratic, we're really only thinking about these 2 dimensions. And yes, we form a square. So later on in the quadratics unit, we're going to be looking specifically at squares. Now, a third degree is cubic. And when you think of cubic, you should actually think about a 3-dimensional figure. So now we have this prism, and I'm going to get rid of the parts that you can't see, but we'll pretend like this is 3-dimensional. And now we have actually a base, a height. So we have a base, a height, and some depth. So this depth is the 3rd dimension. And we think about volume, we think about length times width times height, and different things that are cubic in nature. Now, we can go on and name a 4th degree by saying that it's quartic, and a 5th degree by saying that it's quintic. But really what we're going to focus on this year is our constants, our linear terms, our quadratic terms, and we'll talk a little bit about cubics. Here's where the degree starts to get a little tricky. So 5xy has degree 2. We can ask ourselves, why does 5xy have a degree 2? Well, if x has a degree 1, and I can just write a 1 here, x to the 1 equals x, and y has a degree 1, y to the 1 equals y, then 5xy has an x with degree 1, y with degree 1, and if I add 1 and 1, I'll get 2. So the degree of this is going to be the sum of the powers, and 1 plus 1 is 2. Another example, 12x squared y cubed, has a degree of 5, and it has a degree of 5 for the same reason, because the degree on the x term is 2, the degree on the y term is 3, but this single term, this monomial, 12x squared y cubed, has a degree of 5 because 2 plus 3 is 5. If we recall our exponent properties, we can actually see that x cubed times x to the 5th is equal to x to the 3 plus 5, which is x to the 8. Now, if we have x cubed, which is represented by x times x times x, and we have x to the 5th, which is represented by x times x times x times x times x, we actually have 1, 2, 3, 4, 5, 6, 7, 8 x's, which is our x to the 8th, and we see x to the 8th is equal to x to the 8th. By that same logic, when we have 2 different variables with powers 1 and 2, or 1 and 1 and 1 and 3, we would add them to figure out the degree. Here's a summary. So the expectation is that you can simplify an expression, evaluate an expression for different variables, different values of variables, and that you can name an expression based on its degree and number of terms. So here we have 3x plus 4x squared plus 2x plus 7. Now, if x equals 3, we can evaluate this by saying, substituting the value of 3 for x, so we get 3 times 3 for the 3x term, 4 times 3 squared for the 4x squared term, 2 times 3 for the 2 times x term, plus 7. Now 3 times 3 is 9. 3 squared, because exponents comes before multiplication, is 9. 9 times 4 is 36. 2 times 3 is 6. And the constant 7 stays the same, so we get 9 plus 36, which is 45. 45 plus 6, which is 51, and 51 plus 7, which is 58. So there we have evaluated this expression when x equals 3. Now, when we start to talk about how many terms it has, and naming it by the term and the degree, we'll say that it has one variable. So the variable is x. Now, we know that variables and terms are not directly related, and so because this has one variable, it doesn't tell us much information about how many terms it has. So here, it has 4 terms, but 2 of them are alike. So the 3x term and the 2x term actually have the same degree. They both have a degree of 1. And so because these 2 terms are alike, I want to put them together, and before I put them together, I'm going to rewrite the expression 4x squared plus 3x plus 2x plus 7. And I can simplify 3x plus 2x by combining those like terms and getting 5x to the first power. So here I have 4x squared plus 5x plus 7. So now I have 3 terms. They are not like terms. And because I have 3 terms that are unlike, I have a trinomial. So the name of this expression, if I wanted to name it, I would say by the number of terms, I would say it's a trinomial. Now, if we look individually at the degree of each term, we see that 4x squared has a degree 2 because of the square. We see 5x to the first power has a degree 1 because the power is 1. And 7, no variables, 0 variables has a degree of 0. We'll try to name it by the degree. Now, the term with the highest degree determines the degree of the entire trinomial, and the highest one is 2, so we'll say that this entire thing, because the highest one is 2, is a degree 2, and we name a second degree trinomial quadratic.